Um, Hi everyone, so my name's Amal. I'm a PhD student working with Chantal in the DataFactories, so I'm going to talk to you a little bit about my research. So Chantal mentioned about how we're building a lot of data so that we can understand and predict crystallization behaviour. I'm not going to really talk too much about the Data Factory because she's covered quite a lot of it, but please check out her poster 11 if you want another recap on it. What I do want to focus on is like the data itself. Do you ever look at your data and think, I don't know how reliable my data is in real life? So this is where my PhD comes in. I'm going to be looking at the uncertainties in the data factory and trying to improve the confidence in the data throughout a wide range of APIs and solvents. So what do I mean by sources of uncertainty? So this is anything that causes the measurement to deviate from the true value. So for example, measuring instrument, it can be affected by how sensitive the instrument is, or the way you prepare your samples can also have an effect on the measurement, and even materials can have an effect on the measurement, like the sample for impurities and that kind of thing. So I made a comprehensive list of sources that I've identified throughout the data factory. So please check out my poster 13 to find out more information on that. I'm looking into the uncertainty of solubility measurements by looking at 3 different methods. So visual inspection, so looking at the actual images and finding out the point is where there is complete dissolution and formation of crystals. And comparing that with turbidity, which is like a measurement given by the crystalline software using light transmissivity. And also comparing that to an independent image analysis that was produced by one of our researchers, Christopher Boyle. So please check out his poster number 12 for more information on that. And then check out my poster number 13 for results and discussions. Thank you.
Our next presenter is Dr. Mohammad Salehian. He's a research associate at CMAC, again here at the University of Strathclyde.
Thank you, Alison. Okay, so hello everyone. You've probably seen me from yesterday's DM2 demonstration. I'm going to be in the same place as well at 10:55 in level 3. So I'm a postdoc focusing on the computational modeling and optimization in DM2 platform 2. We try to minimize the experimental load and the development time of the new drug products, mainly focusing on the tablet direct compression. As you see, there are lots of decision parameters that needs to be decided within the development process, including the process settings and formulation attributes. So trying every single scenario, all the combination of these decision parameters is really prohibitively expensive. So we need to design a systematic way with the aid of the DM2 system of the models, which you can see on the top of this graph, which includes mixture models that we use to predict the blend properties using the raw material attributes. Once we have predicted these blend properties, we then use them as an input features along with the process conditions and then feed them to process models to predict the tablet attributes. This system of the models will predict some of the quantities that we need to calculate the objectives of the optimization process. And then the optimization process will decide the next best experiments. We are trying a variety of optimization algorithms, including the global search ones, local search ones, evolutionary algorithms, Bayesian optimization, either exploration-wise or exploitation-wise. And then we decide the next best experiment as a command to the formulation and process development platform, which Faisal shortly explained it to you. So this iterative loop of the feedback continues until we reach the objectives, which has a huge impact on reducing the medicine shortage, waste, and the lead time of development of the new drug products, and increasing the productivity and the patient's healthcare outcomes. We have designed a web interface, including all these models developed so far in the DimaSquare Platform 2, where we demonstrated in level 3 as a part of DimaSquare demonstration. I would be happy to discuss more on the background of the models, including the mechanistic machine learning approaches, all the variety of the models that we are using to develop this system of the models on poster number 23. Thank you very much.
And our next presenter is Hannah Jensey. She's a PhD researcher at CMAC here at the University of Strathclyde.
Hello, I'm going to give you a very brief introduction to my project today, which is developing a next-generation multimodal dissolution testing system for pharmaceutical tablets. I probably should have given it a shorter title. So before we get into exactly what I do, we should think about why I'm doing it and discuss the motivation behind the project. So to get drug release from solid oral dosage forms, disintegration and dissolution has to take place. Now that might sound relatively simple, but these processes and the fundamental mechanisms that underpin them are highly complex. They're synergistic, so there's lots going on at once. And there is an incredible number of factors that can influence these processes. So the overarching aim of this project is to develop this system to be able to further the understanding of these processes. Not only that, but also to look at problem formulations. So if a formulation has given an unexpected result or perhaps failed a step of quality control, this system can be used to assess that. So if we think about how I'm doing this, I've coupled optical coherence tomography, which is a high-resolution, high-speed imaging technique with dissolution apparatus and PAT probes to create this unique system. So one of the key things we wanted to be able to capture was tablet swelling data and disintegration mechanisms. But to be able to do that, we had to be able to hold the tablet off the bottom of the vessel because the imaging is coming in from underneath. So we developed this 3-part sample holder held together with magnets. I think it's important to note that we did a lot of work to make sure the impact of this was minimal on the tablet behaviour. So you've got part A, which would sit in the bottom of the vessel. You would then put the tablet on part B, put the lid, part C on, and all of this would go into part A, which would already be at the bottom of the vessel. And you would obviously start all of the various probes. And that allows us to capture really high quality swelling data. But if we look at the single sample, you can get lots of other data from this single sample. So it is material saving, time saving, reduces an experimental load, as well as giving you so much information about what's going on inside the dissolution vessel. So if you want to see any specific results or have a chat about any of this, I'll be at poster 21 throughout the day.
And our next presenter is Lewis Ross, and Lewis is a PhD researcher at CMAC, again at the University of Strathclyde.
Hello, I'm Lewis, as I've been introduced. I'm a PhD student and I'm in DDMAP, so that's, sorry, forgot I've got a pointer. That's Digital Design and Manufacture of Amorphous Pharmaceuticals, and I'm going to give a brief overview of my PhD, which is the structure and stability production of amorphous pharmaceuticals. So everybody here is well versed on crystalline API, so why bother with amorphous? They have a higher potential energy, so ultimately this can lead to a higher solubility and dissolution in comparison to their crystalline counterparts. However, they do tend to have poor physical stability. So how do we look at fixing this? What we aim to do is we aim to make an amorphous solid dispersion by dissolving the amorphous API within a polymeric matrix. This in turn increases the physical stability and hopefully retains the solubility and dissolution properties. In my project, what we hope to do is we hope to build an amorphous pharmaceuticals database, which will be open access, and we aim to build this to further understand these systems. We aim to build the database up using various DDMAP experiments, such as accelerated stability studies. So I've got a nice little diagram to sort of explain that here, where we put these systems within a storage oven. We store them at 40 degrees Celsius and 75% relative humidity. And we sort of measure autonomously using image analysis the crystallization time. We're also going to build the database up using various measurements, such as thermal or various scattering techniques. So I'll give an example of melting point depression here, which is where as we add more polymer to a system, it reduces the energy in the melting point. Ultimately, we can then use these results and place them into various models, which again, the results will be placed into the database. From this, the overall outcomes that we hope to get is, using all this data, is build predictive models, such as an amorphous stability index, we like to call it, which will allow us to predict these material properties, such as the overall physical stability of the amorphous systems, the glass transition temperature, or the glass formation ability. We also hope to use all these parameters and extract the key governing factors to the amorphous stability. So I'm at poster 19, and I hope to see you in the DDMAP showcase.
And our final flash presentation is from Daniel Powell, and Daniel's a research assistant in CMAC here at Strathclyde.
Hi everyone. So yes, I'm Daniel Powell. I'm also on DDMAP. I'm working on work package 3 of DDMAP. We're looking at in vitro performance prediction of amorphous solid dispersions. So as Lewis just talked about, why we interested in ASDs. Amorphous materials are solid state, but they lack the long-range order of crystalline materials. There's an improved solubility, but reduced stability, and we stabilize these things with polymers. What we're looking at is the dissolution of these ASD products that we get from work package 2 of DDMAP. You can find out more about all of the different work packages at the showcase event. It's just coming up. We're looking at different mechanisms in my work package of release during dissolution. At the moment, I'm just going to show you a little bit about OCT and how we're using that to look at some of these mechanisms. So we've developed a little flow cell, just a simple tool for probing dissolution, and we apply OCT. OCT gives us a cross-sectional view of an amorphous extradate. So you can see here we can get 2D, 3D scans, and we can get data really, really quickly and get really interesting tomography of what's going on inside a sample. So I'll show you this data this is just a nice example of some of the data that we get. So here we have an amorphous extradate of ritonavir and Soluplus, and we can see the liquid penetrating into the extradate and the swelling of the extradate. We also see lots of interesting structural features that we're trying to elucidate and describe more. We have a sort of skin forming on the outside, which disintegrates, leading to a rapid disintegration event. And then we end up with a sort of steady state dissolution, and we can see material transport occurring through the sample during the experiment using optical coherence tomography. So it's really interesting technique, gives us lots of information, and we can also see other sort of particulates that are in the sample. So it really gives us a huge amount of information to process and a lot of questions that we need to answer. So we're working on integrating other techniques, dissolution techniques, low-frequency ramming, to further elucidate what's going on inside a sample like this. Ultimately, the goal would be to integrate a variety of different process analytical technologies to monitor dissolution of these amorphous extradates and elucidate all of these different mechanistic processes. Ideally, this is the DataFactories talks, so ideally we can turn this into a high throughput system where we're doing lots of dissolutions in a short space of time and getting lots of data to feed into the amorphous pharmaceuticals database that Lewis has just mentioned. So thanks for listening. If you want to ask me any questions, you can come to the showcase, which is just after, or you can visit me at poster 17. Thanks very much.
Thanks, Daniel. And thank you in particular to our all 5 of our flash presenters, so Amal, Mohammed, Hannah, Lewis and Daniel. Thank you very much for that.